Good morning, everyone, and welcome to the BRNE 600 webinar covering separator sizing. My name is Assis Patel, and I will be your host for this webinar. Otherwise, the goal of this webinar is just to give you a brief overview on how you can access the separator sizing in ProMax, what input information you'll need, and what results are provided, in addition to discussing the results and seeing how you can interpret what ProMax is actually telling you. And we'll do this by looking at one case where we'll have a two-phase separator, and we'll compare that and also comparing a three-phase separator scenario. So just a general overview. Our overview is going to be over separator sizing inputs and outputs, and then we're going to be comparing a vertical versus horizontal two-phase separator. And for our three-phase separator comparison, we're going to be comparing a horizontal separator with a Weir versus a horizontal separator with a bucket. So if you are in ProMax, the first thing that you want to do in order to size a separator is to, one, make sure that your separator is going to be converged. Once it is converged, you're able to open up the separator in the project viewer and enable separator sizing by going to the process data tab and checking on the separator sizing checkbox, which is going to activate a sizing tab, which is where we're going to put the rest of our inputs. And this is something that we will take a look at after we complete the presentation. I'll actually pull up a simulation and we'll go through sizing some things. So the types of separators that you can size in ProMax are listed over here on the right. You have a vertical two-phase, vertical three-phase, a horizontal two and three-phase, and then a few different configurations of horizontal three phases. One other important thing to know whenever you're sizing something in ProMax, the separator that you're sizing, if you wanted to size a three-phase separator, it must have three active outlets. It can't just have three outlet streams and one of them not actually have any flow in it. Otherwise, that'll interfere with the calculations that need to take place. So if you only have a liquid and a vapor coming out of a separator, you have to size it as a two-phase separator. But if you have two liquids and a vapor, then you can size it as a three-phase separator. So for two-phase separator sizings, the first type of input that you will need, regardless of whether or not the separator is vertical or horizontal, is going to be either the vapor-liquid droplet diameter, the vapor-liquid K, which refers to the solder's brown K, and the terminal velocity in the vapor. If you do not provide any of these, ProMax by default is going to calculate what the vapor-liquid K value should be based on your composition of your gas. This is important because it's going to determine what the terminal velocity of the vapor is, which is going to determine how much space or volume you would need for any light liquid droplets to separate out of the vapor phase and in order for the vapor to be fully disengaged from the liquid. The next input that you will need is going to be either the light liquid holdup time or the light liquid holdup depth. These are going to correspond to either the time that it would take for your molecule. And if we take a look on the next slide here, we have the liquid holdup depth, which is going to correspond with that light liquid holdup time as being the time that it would take for a molecule to travel from the normal liquid level in the separator down to the low liquid level in the separator. Or alternatively, whenever the depth is calculated, it is going to be the height from the normal liquid level to the low liquid level, and then the volume is going to be calculated once ProMax determines what the overall volume of the vessel is. Then you'll also need the surge time, which is going to correspond to the light liquid surge depth. If we take a look on our diagram here, the surge depth is going to be the height from the normal liquid level up to the high liquid level, or in other words, the amount of time that it would take for a light liquid particle to travel from the high liquid level down to the normal liquid level. And then you'll need a light liquid low level shutdown depth, which just corresponds to the height from the seam end of the separator up to the low liquid level. And those three heights are going to correspond to the overall light liquid residence time in a 2-phase separator. And this is going to look a little bit different in a 3-phase separator, but we will get to that. The next set of inputs that you can specify is going to be a demister pad thickness and the demister pad overhead clearance. By default in ProMax, there is no demister pad thickness specified. So ProMax treats it as if the separator does not have a demister pad. If the demister pad thickness is specified, then ProMax will account for making sure it has enough space in the top part of the separator to account for the demister pad and the overhead clearance of that demister pad. ProMax does not rate demister pads. So if you specify that there's a demister pad there, it's not rating the performance of that pad. The specification of a demister pad is going to cause a change in the K value, but otherwise doesn't impact the separation. It will only impact the results in making sure that there is enough space at the top of the separator, like shown in the diagram here. So if you didn't have a demister pad thickness specified, ProMax would not include this height. But if you do, then it'll include height for the demister pad thickness and the demister pad overhead clearance. Our final inputs are going to be the minimum vapor disengagement depth and the vapor disengagement depth. So you do not need to specify a minimum vapor disengagement depth, but you can. Otherwise, ProMax, based on your vapor liquid K value, is going to calculate what the vapor disengagement depth will need to be in order for our vapor to successfully disengage from the light liquid and have enough space to, and also for the light liquid to have enough time to drop out of the vapor. And that's going to correspond to the height between the inlet and the demister pad if it is present. If the demister pad is not present, then it'll simply be the height from the inlet to the top seam. The minimum vapor disengagement depth, if it is specified, is going to limit how small this value can get. So if ProMax calculates that your vapor disengagement depth needs to be 2.5 feet, but you have a minimum vapor disengagement depth of 3 feet, then ProMax will override the calculated value with your minimum instead. Whenever ProMax is calculating the volume of your separator, or whenever it's sizing your separator, what it's actually trying to do is an optimization equation where it's trying to minimize your overall volume. So it's going to work on first setting a diameter, and a length that's going to be somewhere between the minimum and maximum shell L over D ratio. By default, the minimum ratio is 1.5 to a value of 6 as the maximum shell L over D ratio. So the shell length is just referring to the length of the vessel from one seam to the other seam. It's not going to account for the length of the vessel that is part of the headspace. And additionally, ProMax, while it will report a total vessel height and a total vessel volume that accounts for this space, whenever we are taking a look at the separation that is occurring, we do not consider the fluid to flow in the headspace. There are some additional parameters that you can input that do not have an impact on the sizing of the separator, but have more to do with additional calculations, such as how thick the separator is going to be, such as the design temperature and the maximum allowable working pressure. Based on these inputs, ProMax is going to set how thick your vessel is, and based on additional inputs such as the corrosion allowance and your shell and head material of construction, that's going to determine how much mass your separator weighs, which will be a calculated output. The only other input here is going to be the head type. So you have 3 different options in ProMax. You have the ellipsoidal, toruspherical, and a hemispherical. These are all going to impact the total vessel volume, but won't impact your sizing calculations in terms of separation, because they are included outside of the shell length. And the one that you pick is going to primarily be based on your application of how high of a pressure system that you are running. And then the final outputted results that you're going to be taking a look at for a two-phase separator include the vessel inside diameter, which is going to be calculated, the shell height, which will also be calculated. And if you need to fix one of the two, you are able to fix the vessel inside diameter, but you're not able to fix the shell height. Then the shell L over D ratio will be reported, and it'll be somewhere between the maximum and minimum values that you have set. The total vessel height, which is going to include the additional height between the shell seams and the heads of the separator, and the feed nozzle distance above surge, which for a vertical two-phase separator is the distance between the high liquid level and the middle of your inlet nozzle. The vessel internal volume, which is what ProMax is trying to minimize. The vessel mass, which is going to be reliant upon the material of construction and the thickness. And then the vessel mass filled with water, which is going to give you an approximation of how much the vessel would weigh at the heaviest if it was to be filled up with some form of liquid. This is a look at a two-phase horizontal separator, so you'll see some similar inputs and similar outputs here. We'll still have the same shell length, however, instead of going from up to down, it's going to now be going from one seam to the other seam. And then our diameter is instead going to be the overall height of our vessel in a horizontal case. But we still have that same vapor disengagement depth. We're going to have our demister pad thickness and our demister pad clearance height if necessary. But now you'll notice that the demister pad clearance and demister pad thickness are part of the overall vapor disengagement depth, whereas in the vertical separator, they were just all three of these made up the vapor space. We still have our high liquid level, our normal liquid level, and our low liquid level. So we have our low level shutdown depth being the distance from the bottom of the separator to the low liquid level, the low liquid holdup depth being from the low liquid level up to the normal liquid level, and the liquid surge depth being from the normal liquid level up to the high liquid level. In a vertical separator, you are not required to input in the corrosion allowance or the material of construction in order for ProMax to calculate the results. However, for a two-phase separator, you will be required to specify our corrosion allowance and the material of construction for both the shell and the head. And one important thing to note before moving on to our three-phase separators is that what we looked at were some of our inputs that are going to impact the result, but for a vertical two-phase separator, there's going to be defaults input in for that light liquid holdup time, the surge time, and the low-level shutdown depth, as well as for a horizontal two-phase separator. And ProMax, by default, will be able to calculate some vapor liquid K. If you didn't want to put any specifications, you wouldn't have to for a vertical separator. Of course, this wouldn't give you the best results regarding your own separator, because your own separator might have different time requirements. But if you just want to do a quick test, ProMax does have defaults put in there for two phases, and as well as for a horizontal two-phase, except you would need to input in a corrosion allowance and a material construction, because those are not there by default. Now moving on to a three-phase separator. Now we're still going to have the same inputs regarding our vapor space. So the vapor disengagement depth, the demister pad thickness, the demister pad clearance, and we're going to have our light liquid specifications, such as our light liquid surge time, our light liquid holdup time. But in addition, since we have that third phase, we're also going to have similar parameters for our heavy liquid, depending on what type of separator we have. In the simulations after this presentation that we're going to take a look at, we are going to be sizing a three-phase separator with a Weir and a three-phase separator with a boot. So the inputs that we're going to be looking at are going to be associated with those two cases. And if you need to size a different type of separator, you are more than welcome to send our support an email or give us a call, and we can talk through that form of separator. So for a three-phase separator, in addition to our vapor liquid K, we now need to provide a separation parameter for our liquids separating out. This is going to be the liquid-liquid droplet diameter, or the liquid-liquid C, or the terminal velocity in the light liquid and the terminal velocity in the heavy liquid. It's important to note that if you want the liquid-liquid droplet diameter, or in other words, the separation time from the terminal velocities of the light liquid and the heavy liquid to be different, you would need to specify individual terminal velocities for the light liquid and terminal velocities in the heavy liquid, which would correspond to two different sizes of liquid droplets separating out of either phase. If you specify a liquid-liquid droplet diameter or a liquid-liquid C, that would set the same droplet diameter for a heavy liquid, that is, leaving the light liquid phase, and for a light liquid, that would be leaving the heavy liquid phase. Additionally, this time we're going to be setting the light liquid residence time and the heavy liquid residence time. There are some recommendations for those parameters based on in our help that are taken from GPSA. For most applications, it's going to be somewhere around 5 to 10 minutes for typical hydrocarbon separation, but there are ranges. This light liquid residence time and heavy liquid residence time are going to refer to the amount of time that the liquids spend in the settling compartment of our separator, and that's going to correspond to the light liquid settling depth and the heavy liquid settling depth on this diagram. So if we take a look at our three-phase horizontal separator with a Weir, we have the settling compartment in the first portion, and then if we look at the other side of the Weir here, we have the holding compartment of our separator. So that's where we have our light liquid surge depth and our light liquid holdup depth, as well as the light liquid low-level shutdown depth. But we also have the light liquid settling depth and the heavy liquid settling depth, and these two correspond to our residence time specification. So since there is no additional storage compartment for a heavy liquid in this type of separator, we don't have a heavy liquid surge or holdup depth, and we only have those for the light liquid. So the residence time in this three-phase separator doesn't stand for how much time the liquid stays in the separator, so much as how much time it stays in the settling compartment. If you wanted to know the total time that the light liquid would end up spending in the vessel, you'd have to add the light liquid residence time to the light liquid holdup and surge time. And in the other three-phase separator that we're going to look at is going to be with a boot. So here we still have our light liquid surge time and our light liquid holdup time parameters represented in terms of their depths, and we have a smaller portion for our heavy liquid, and that's still going to get a settling depth as well as the light liquid, so we still need our residence time specifications in this case. But now the holding compartment is simply the top portion of our horizontal separator, and we don't have that low-level shutdown depth. And then the residence time would correspond to the amount of time that the liquid spends, the light liquid, at the very bottom of the separator and into however much the interface would be. It's important to note that for a separator with a boot, your interface is going to need to be somewhere below the bottom of the vessel, and the heavy liquid residence time is going to be at the very bottom of the vessel. So in terms of results, you will still get the same results for a three-phase separator. You're going to get your diameter, you're going to get the length, you're going to get the overall volume and mass. But for a three-phase separator with a Weir, you're also going to get a few other lengths, because now we have our separator separated into a few different components. We have the settling compartment length, which is going to be the length of the overall settling compartment. Then you have your Weir height, which is going to be the sum of both the heavy liquid settling depth and the light liquid settling depth. And you are given the length of your light liquid bucket. So if you're trying to make sure that the separator in ProMax represents your separator, you can play around with the different residence time and holdup and surge time specifications to make it such that your settling compartment length and your light liquid bucket length match the separator that you actually have, as well as changing these two parameters, the settling depths, which would be represented by the residence times to keep the weir height to what you would want. Now with the boot, or the three-phase separator with a boot, you'd get the same results, but you would also have the boot shell length, and the light liquid interface in boot is going to be a toggle option to determine whether or not it actually goes into the boot or whether it's just above. And if it does go into the boot, how far does the light liquid go into the boot, which is going to be represented by this depth here. And ultimately, you will get a volume for the boot that's going to be reported by this boot shell length, and that will correspond to the that will contribute, to the overall volume of the vessel, but the head space will not, similar to how the head space in the regular portion of the separator does not. And it's important to note that you will need to provide a material of construction for the shell of the boot and the head of the boot. So the first simulation that we're going to take a look at is an amine sweetening unit, but what we're going to focus on is sizing the flash tank as part of the amine unit. For those of you unfamiliar with an amine unit, what an amine system is it allows us to pick up sour components in our gas that is unclean. So if you've gotten gas from a well site that contains H2S CO2, then you're going to use, or you can use, an amine to pick up the H2S and CO2 out of the gas. But as a result of the amine, which is basically a weak base and water solution, that amine is also going to pick up some hydrocarbons. It's not going to pick up a huge amount of hydrocarbon because it's an aqueous solvent, so it has a low affinity for hydrocarbons, but it's going to pick up some. And as a result, we would like to flash out those hydrocarbons. So we send our amine, after it picks up the acid gas components, to a flash tank, which flashes out the hydrocarbons while still keeping the acid gas, inside of the amine phase. So here we primarily have a liquid going in, and the majority of our flow coming out is going to be a liquid. As we see here, the mole fraction vapor in this separator is only 0.15%. So we don't really need a whole lot of area for our vapor in this separator. So with that in mind, we're going to first double click on the flash tank. And then to enable separator sizing, we go over to the process data tab and we check on the include separator sizing option. And then that reveals a sizing tab, which I can click on and start making specifications for. So first, I'm going to perform the sizing for a vertical two-phase separator. So in my type dropdown, I'm going to click on the drop-down arrow, scroll up and choose vertical two-phase. And at this point, I would be able to click solve here on the bottom, and ProMax will give me my results. But I'm going to make some inputs in our parameters list here, based on one of our exercises from our ProMax 232 course, which covers separator sizing as well as different sizing and rating in ProMax. But since we're going to need our material of construction for whenever we test a horizontal case, I'll go ahead and specify our material of construction. I'm also going to make sure that we have a corrosion allowance specified and that ProMax knows to include space for a Demister pad. So what I'll do here is first, I'll see my Demister pad thickness. I'm going to specify 6 inches. That's going to cause ProMax to take into account for the fact that we now have a 6-inch space for our Demister pad and incorporate the 1 foot or 12 inches for the Demister pad overhead clearance. Additionally, you'll see here that we already have a light liquid holdup time by default of 5 minutes and a light liquid surge time of 2.5 minutes. ProMax by default would specify a vapor liquid K but for the meantime, I'll just say that we have a 150 micron vapor liquid droplet diameter. And then at the bottom, I'm going to make sure my head type is set to torus spherical because this is a low pressure case, so we wouldn't necessarily need a different type of head, as a torus spherical head type is more than capable of withstanding low pressure scenarios. Then I'll specify a corrosion allowance of 0.01, which is going to contribute to the calculation of my shell and head thickness. And then for the material of construction, I'm going to specify carbon steel for both the shell and the head. I can do this by first clicking on the material of construction box, clicking on the down arrow that pops up in the top right-hand corner of that input box, and then in the following material of construction selection window, making sure I have my groups displayed set to steel and ferrous alloys at the top. And I'm going to be adding in carbon steel A10C grade B, or 106, sorry, excuse me, grade B for the material of construction for the shell. And I'll click OK. And for the head material of construction, can be specified in the same way. Click on the box, click on the arrow in the top right-hand corner, and in the resulting material of construction selection box, make sure you have the right group selected. And for this, I'm going to select carbon steel A105 and click OK. And this will allow us to calculate our vessel inside diameter, the height, and what the volume would be if it was a vertical two-phase separator based on our other default inputs. So I'm just going to go ahead and click the solve button in the bottom. And for our vertical two-phase separator, it looks like the height would be 24.6 feet. Our inside diameter is reported as 4.5 feet. And that would bring us to a total vessel internal volume of 407 feet cubed. And now we can compare what that would look like as a horizontal two-phase separator with the same requirements for our Demister pad, as well as the same time requirements for the holdup time, the surge time, and given the same vapor liquid droplet diameter. So we can make a comparison of these two separators and see which configuration is ultimately going to cause us to have a smaller separator, which is going to be cheaper to obtain. So we'll go from vertical two-phase to horizontal two-phase. And it saved the inputs that we had. So we can come down to the bottom and click solve again. In this case, we get a vessel inside diameter of 7 feet. We get a shell length of 12.4 feet. And we have a vessel internal volume of 3,030 feet cubed. So in this case, we would most likely like to use our vertical separator because of just based off your vessel internal volume results, while the height of our other vessel was taller, which means we might need some kind of support for that. It was also significantly smaller in terms of the diameter, which is going to impact the volume more so. And so this vessel would be a lot smaller and therefore be cheaper if we're looking at a vertical case, as opposed to looking at the horizontal case. And the reason for these different results is if we went back and took a look at those diagrams, and we can actually access those diagrams I was taking a look at by going to the ProMax help. So the way to access that is if you click anywhere on this list, like I've just selected design temperature, denoted by the highlighted black outline, I can then press F1 on my keyboard, and this will open up the ProMax help to the page of whatever I had selected. So since I had a separator sizing parameter selected, it opened the separator sizing parameter page. And if I scroll through this help page, the first thing that it's going to tell me is the minimum required parameters. So for example, for my vertical two-phase separator, I did not need any additional separator parameters, but for the horizontal, we would have needed our corrosion allowance and our shell and head material construction. And then it actually goes to a sizing parameters, which will define all of the different terms that are in that list. So if you forgot what the light liquid holdup time is, you could click on the green text for it, and it would tell you that it is the time that it takes to reduce the light liquid level from normal operation to empty while maintaining a normal outlet flow without any extra feed, and that it corresponds to the light liquid holdup depth, and that the default is 5 minutes. Then if you ever forgot where these parameters specified to an actual diagram, you could click on one of these blue hyperlinks. For example, our vertical two-phase, we see that our light liquid holdup depth or holdup time would correspond to this height here. And in our horizontal two-phase, it would correspond to the same difference in height, but stretched over a longer area. So in this case, because we don't have that much vapor that's actually forming from our liquid, we don't need a long length or a large volume for our light liquid surge and hold up times in order for that vapor to leave. So in this case, a vertical separator makes more sense because since there's not much vapor, we don't actually need that much overall volume or time for our two-phase solution to go in and for our vapor and our liquid to sufficiently separate out. So now we're going to move on from a two-phase situation over to a three-phase. So in this three-phase situation, what we're taking a look at is going to be a solvent-enhanced glycol dehydration unit. For those of you unfamiliar with glycol dehydration units, they are a liquid solvent that is used to pick up water content in gas. So in a wet gas, so after you go through an amine unit, typically that gas, once it's rid of its H2S and its CO2, is saturated with water, and that will also need to be removed. So it gets sent to a glycol dehydration unit where it's brought into contact with the glycol solution to pick up the water and reduce it to pipeline quality, which means somewhere around typically 2 to 7 pounds of water per million standard cubic feet of gas. But what we're going to be taking a look at is more of a process variation of a typical unit because it's using some solvent to help regenerate our glycol, which is basically going to make it better at removing water. But process information aside, what we're looking at is this solvent flash drum, which takes in our overheads from our glycol regenerator. So whenever we're generating our glycol, we're boiling off the water. And so the majority of what's being sent into the solvent flash drum from our vessel's regenerator is going to be the light liquid, as well as our vapor from the overhead here. And we can take a look at what that is if we double click on both of these inlet streams. So if I double click on stream 10, we see that this is 100% light liquid, and we have about 823 pounds per hour of our light liquid. And if we take a look at the composition, we see that it's mostly heavy hydrocarbons as well as BTEX components, which is not atypical for TEG. For those of you familiar with TEG units, you know that the TEG, while also picking up water, is well known to have a higher affinity for heavy hydrocarbons, and as a result, we end up with those BTEX components. So we have 800 pounds of heavier hydrocarbons going in, and also some water, but not very much in that stream. And then we can check on stream 9, which would be the overhead vapor after it's been condensed partially. So we see this stream is split a few ways. It has a little bit of vapor, it has some light liquid, and it has some heavy liquid. And if we take a look at the composition, the vapor is primarily going to be our lighter hydrocarbons. The heavy liquid is effectively all water, and our light liquid is more of those BTEX components. And in terms of flow rate, we have 74 pounds of vapor and another about 1,900 pounds per hour of light liquid and about 500 pounds per hour of heavy liquid. So whenever we think about all that's going into this solvent flash before we size it, it's about 2,600 pounds per hour of light liquid, 75 pounds per hour of vapor, and about 500 pounds per hour of heavy liquid, which is going to result in 3 phases being separated out, and therefore us needing this 3-phase separator. So since we have 3 phases actually coming out of our separator, we can size it for 3 phases. So first I'll double click on the separator. I'll go over to the process data tab, and I'm going to check on the include separator sizing option, which is going to reveal the sizing tab. The first thing that I'm going to do is to change my vessel type over from horizontal 2-phase to a horizontal 3-phase with Weir first. I'm going to provide the same vapor liquid droplet diameter that we had earlier at 150 microns. In terms of our light liquid droplet diameter, which would be our next input, which is required for 3-phase separation, I'm going to not specify, but by default, ProMax is going to assume a droplet diameter of 100 microns there. Our light liquid holdup time and our light liquid surge time are already specified at their default values. In this case, we're going to say that there's not a demister pad, so by leaving the demister pad thickness specification blank, it's going to not need to include any extra space for the demister pad or the overhead clearance of that demister pad. Then the next inputs that we're going to need is going to be the light liquid and heavy liquid residence time. So I'll scroll down and I can find these values here. So for our 3-phase separator, I'm going to specify a light liquid residence time and a heavy liquid residence time of 10 minutes each. And actually for our vapor liquid K, I'm going to let that automatically be calculated in this case. So I'm just going to delete that specification of the droplet diameter, and I'll let ProMax handle the calculations of this. And if we look at the bottom here, it will not let us click solve yet, and it'll actually provide an error telling us what specification we have missing. So here it says a material of construction or corrosion allowance has not been specified. So I know that I need to provide a material of construction and corrosion allowance. So I'll continue scrolling down. I can leave my head type as toruspherical. For my corrosion allowance, I'm going to go ahead and specify 0.005 inches. For the shell material of construction, this is also going to be A106 carbon steel grade B. So I'll click on the arrow in the top right-hand corner of the shell material of construction box and select grade B A106. Click OK. And for my head material of construction, I'll do the same thing. Click on that arrow, but this time select A105 and click OK. And now you'll notice that the solve is available. It's not grayed out anymore and we have no more errors. So with a combination of the defaults that ProMax has provided and the inputs we put in, we are able to solve for our separator sizing. So for our Weir case, we'll see that the vessel's inside diameter ends up being 3 feet. The length of our vessel is 5.3 feet. And the vessel's internal volume is going to be 194 feet cubed. And if you take a look at the bottom, you'll notice there's a warning saying that the separator length is being controlled by liquid holdup and or residence times requirements. So that warning means is that one of our holdup times or residence times is acting as the most important variable in the minimization function. So if we reduce one of those variables, it should change the overall predicted size or volume of our vessel. And if we played around with changing our light liquid residence times and our heavy liquid residence times, we should be able to see that. So let's see if we drop our light liquid down to 5 minutes, what happens. So whenever I changed it down to 5 minutes, we'll see that the vessel inside diameter got reduced to 2.5 feet. The shell length was increased to 13 feet, and our vessel's internal volume was overall reduced down to 142 feet cubed. The only reason I changed that residence time was just to demonstrate what this warning actually means. If you see it whenever you're performing your own separator sizing, it just means that one of these parameters has control over what the vessel's current volume is. I'm going to change that back to 10. And now I'm going to click solve again so we can take a look at some of the additional outputs that we got for a Weir. You'll notice here we have our length of our settling compartment and we have the length of the liquid bucket. So our overall 5.3 feet is partitioned into two sections. 2.1 feet for the settling compartment, which is where the residence times correspond to, and then for the light liquid that's being held, or in the holding compartment, we have about 3.2 feet of that space, which is by our light liquid surge time and our light liquid holdup time. So if that proportion seems off to you in what you would expect for this, then you would want to, if you wanted it to be larger in terms of the settling compartment, we'd want to increase our residence time. If we wanted our holding compartment to be smaller, we would need to decrease our light liquid holdup time and our light liquid surge time. But also, we would need to fix the diameter. Because if we don't fix the diameter of the vessel, then ProMax does have the option to just change the diameter, and that may end up with providing us different lengths. So, for example, whenever I reduced the residence time down to 5 minutes, you'll notice that the length actually got longer, despite us needing less residence time, but that's because the vessel's diameter also was able to decrease and adjust for that in order to give us a smaller overall volume. So let's say I fix my vessel inside diameter at 3 feet, and I decrease my residence time for my light liquid down to 5 feet, or sorry, 5 minutes for both my light liquid and heavy liquid. And I click solve here. Oh, well, those are too small. Let's just try 9 for both. And at 9 feet, so you'll notice that if things are too small, the separator sizing may not work. So you can be either, you can input in a minimum. There's basically two failure cases, in one in which your parameters are too small and it won't work out for your separation. Additionally, there is a case where if you set a minimum and the calculation still provides your result, but with a higher value, it'll tell you in the bottom, it'll say, hey, your residence time of, let's say, 2 minutes is too small. The actual residence time needed to be 6 minutes. And that's just to let you know ProMax went ahead and changed that value for you whenever it performed the calculations. But looking back at the effect of our residence time, whenever we have fixed our vessel inside diameter, we'll see that the overall length decreased slightly here from 5.3 feet down to 5 feet because we made the overall settling compartment a little bit smaller while fixing our vessel's inside diameter. So it couldn't change the diameter instead, and it just had to mess with the difference between the length of the settling compartment and the light liquid bucket length. And that's going to cover it for the Weir case. So let's go ahead and take a look at our horizontal three-phase with boot. So here, we keep all of the default parameters that we have specified. I'm going to bump these back up to 10. And the other things that we will need to specify for a boot are going to be told to us here at the bottom. It's going to say material construction or corrosion allowance has not been specified. We know we have that for our head and our shell, so that means we also need it for our boot. And so in this case, our boot's shell material of construction is going to be the same as the shell of the separator. So what I'm going to do is click on the shell material of construction, press Ctrl-C to copy, and in the boot, I'm going to press Ctrl-V to paste, and I'm going to do the same thing with the head material of construction and the boot head material of construction. I'm going to delete this fixed value for our vessel inside diameter. And I'm going to leave the liquid-liquid interface in boot option turned on and say that it is about 0.5 feet into the boot, and click solve. In this case, we get that our diameter would be 2.5 feet. We see that the length of our vessel is going to be 5.22 feet, and that the vessel internal volume would be 30 feet cubed. So in this case, our boot is going to give us the overall smaller separator. And this is because now that we didn't actually need that extra liquid bucket to hold our light liquid, we would have had, if we just gave more space to simply the settling compartment, that would give enough space for the heavy liquid and the light liquid to separate out appropriately. And we would only need the boot for the heavy liquid to reside while it's separating out, because if you remember, our heavy liquid to light liquid ratio heavily favors our light liquid in this case, because we have a lot more of our light liquid. So just for this set of process conditions, the boot would be the more optimal separator to choose in terms of the overall in minimizing the volume. However, you would have to consider the space requirement for that boot and to see if it was able to fit wherever the solvent flash drum would go, and to also think about the support for that portion of the boot. Because the Weir would be a regular separator, but you need some extra space at the bottom corresponding to the boot shell length here, which would be 2.1 feet, and the total length, including the head, would be an additional about 2.3 feet of space at the very bottom of the separator. So the vessel's inside this diameter would be 2.5 feet. So that boot portion would be about as long as, in terms of height, as the vessel. So those are other factors to consider just beyond the volume. But if we're just comparing volume to volume here, the boot would win out, because we have more horizontal space for our liquid to separate out. So we have more volume for that residence time requirement to happen, and we're not sacrificing some of it for holding up the liquid, because the light liquid in the boot configuration is just the space on top of the heavy light liquid interface. So that is going to conclude the webinar for the separator sizing. I hope that you are able to take away how you can size separators in ProMax, as well as how you can analyze and interpret the results. If you are interested in learning more about the separator sizing, you can, of course, email us at support@bre.com and ask whatever questions you have there, or for getting assistance with sizing one of your separators. You're also more than welcome to call our number at 979-776-5220 to talk with one of us about separator sizing, or if you'd like assistance with sizing one of your own separators. Thank you for attending the webinar, and have a great rest of your day.